Hey, so we're going to be talking about the isoelectric point, or PI as it's abbreviated. Now, the isoelectric point is the point along the pH scale at which a molecule, and in this case we're going to be talking about an amino acid, exists in a neutral form with zero charge. In other words, it is neither positively nor negatively charged overall. It is isoelectric. And iso means equal. And it's nice to know the isoelectric point for an amino acid because then we can predict whether or not it will be charged at a certain pH. And who doesn't want the power of prediction? So how do we figure out the isoelectric point for an amino acid? Well, let's start with the generic amino acid structure here. So now let's take a look at the two functional groups on this amino acid. Ignoring the R group, or the side chain for the time being, we're going to be talking about the amino group and the carboxylic acid group. So the amino group here, it has this nitrogen, which is a very happy proton acceptor. So we're going to write that here. And because it's a happy proton acceptor, it is considered to be basic. And we've drawn it out in its protonated form here after it's accepted an extra hydrogen, or proton. So now, coming over to our carboxylic acid group, this group is a very willing proton donor. And because it is a proton donor, we call this acidic. And so we've drawn it out here after it's already donated its proton, so it has a negative charge. And now looking at the overall net charge of our amino acid, we can see that we have a positive charge here and a negative charge here, and so the overall charge is 0. And we have a special name for when you have a molecule that has both a positive and a negative charge present. And that special word is called a Zwitterion, which comes from the German word for hybrid. So now what would happen if we take our amino acid and we put it into a solution that is a very low pH, say a pH of 1? In other words, an acidic solution. Well, we can think of acidic solutions as having a lot of excess protons around. So anything that can be protonated on our amino acid is going to be protonated. And so it's going to look like this. And now if you take a look at both of the groups on our amino acid, you can see that our amino group is still in its protonated form and carries a positive charge. But now our carboxylic acid group has gained a proton and lost its negative charge. And now you can see that the overall net charge on this molecule is now positive 1. So now let's come over to the other end of the spectrum. Let's put our amino acid in a solution with a very high pH, say a pH of 12. And so this is going to be a really basic solution, and we can think of really basic solutions as having a lot of excess hydroxide anions around. And so now everything that can be deprotonated on our amino acid will be. So it's going to look like this. And if we look at our overall net charge of our amino acid now, our amino group has been deprotonated, so now it is neutral, and the carboxylic acid group has been deprotonated, and so it has a negative charge again, and so it has an overall net charge of -1. So now we know that we have a range of forms that our amino acid can take. We have the positively charged version at low pHs all the way up to the negatively charged version at high pHs. Now back to our question about the isoelectric point. So the isoelectric point is the pH at which we go from the positive to the negative form. In other words, it's where we find the Zwitterion. And to find out the exact pH, we have to take the average of the pKa's of our two functional groups. And recall that the pKa is just the negative log of the acid dissociation constant. So on average, and it varies between all the different amino acids, but on average, the amino group has a pKa of around 9. And then on average, the pKa for the carboxylic acid group is right around 2. So now if we just give ourselves a little bit more room here, we can calculate what the PI, or isoelectric point, would be for our generic amino acid. So taking the average pKa for the amino group, and then the average pKa for the carboxylic acid group, and we divide by 2, then we get 11 over 2, and we come to an isoelectric point of 5.5. But say our amino acid has a side chain or an R group that is also a functional group. Then we would also have to take the pKa for that group into account when we calculate the isoelectric point. So what have we learned? Well, we learned that the isoelectric point is the pH at which a molecule is found in neutral form. In this case, when an amino acid is in its Zwitterion form. And we also learned how to calculate this isoelectric point for an amino acid by taking the average of the pKa's of all the functional groups in that amino acid.